Okay, folks, good morning. Final day of the class. I guess this is the day that you all have been praying for. It's finally here. So we had a quiz last time. I'm going to go through the solution of this quiz. By the way, I have graded the quiz, so I have it here. After the class, I can return it back to you. Also, the grades file on Blackboard reflects all of your 7 quizzes. What I'm going to do this afternoon is I'm going to look at your attendance record and also update that file with your basically almost final grade if you choose not to take the final test. Now in that file that you're going to see later this afternoon or maybe tomorrow morning, there is a bunch of columns for the final exam, but because I don't know who is going to take the final and who is not, I'm just going to assume nobody's not going to take the final exam. So there's going to be a bunch of zeros in there. So don't be surprised if you see the zeros. But then the file is programmed in a way that you can actually pretend that you are going to take the final exam and put your score over there and see how it is going to impact your overall grade if you choose to take the final. And remember, the final has 30 points. Okay, regarding the quiz, we had this topology over here, which is a zero current switching buck converter, and the input current waveform or the current of the resonating inductor is provided, and the peak value of this current is 18 amps. So referring to your notes, you would know that this peak is basically something like this, and I out is 7. So we got to find a value for Z naught, which turns out to be 2. And since we are here, we can also calculate omega naught, the resonance frequency, because we are going to need it later. And this turns out to be 1 basically megaradians per second. All right. So now this is 2. The whole thing is 18. So this will give you a VN of 22 volts. All right. So now that we have the value of the DC value of the source, we can continue with, ultimately we want to find the output voltage. So we can continue with finding the duration of T1. T1 is the time that it takes for the input current or for the inductor current to rise linearly from 0 to I out. So basically this time span over here. So T1 is I out times LR over Vn. Now we have pretty much everything. 7 times 2 microhenries over 22 volts. That would give us 0.6364 microseconds. It's a relatively short time. And then for T2 we had this expression that T2 is T1 plus, or you can calculate T2 minus T1, it doesn't really matter. The inverse sine of so technically T2 is when the resonance is over, meaning that the current basically returns back to 0. Okay, the current of the resonating inductor. And this turns out to be 4.468 microseconds. A lot of you guys made mistakes. I don't know. The equation was correct, but the number that you put in front of that, it was not correct. I don't know what happened. If maybe the calculator had some flaws or something. And then ultimately T3. T3 is not really shown over here, but T3 is the time that the voltage across the diode is actually getting discharged. So it's basically reducing down to 0. It is T2 plus and this turns out to be 7.251 microseconds. So we have all of the information that we need to find the output voltage. And remember, the equation was V out over V, and so I'm writing V in over here, over T times T3 minus T1 over 2. Here, because I have T1 and T3, I wrote it this way, or you can write T3 minus T1 plus T2 minus T1, something like that. And this turns out to be 15.253 volts. Obviously, the output voltage should be smaller than the input voltage. It's a buck converter in the end. And some mistakes that you guys made. One common mistake was instead of T over here, a few of you guys placed actually T3 over here, which is actually not the right way of doing it. So don't do that. And some of you actually, instead of using the equations for the ZCS buck, you use the equations for ZVS buck. So please make a distinction between the two topologies. All right, any questions? Okay, so as I said, I have it graded over here. After the class is over, I can hand it back to you. One thing that I noticed after the class was done was I kind of made a mistake when I was drawing these waveforms last time for the okay, basically the waveform that I drew over here is not correct, and I'm going to draw the right one over here. The mistake that I made was the frequency of the current is actually half the frequency of my VCD, which is not correct. Actually, they should be in the same frequency, so the correct one should be something like this. All right, something like that. All right, now before getting to there, let me actually go through the topologies that we have analyzed so far, as long as Chapter 9 is concerned. First, we looked at this one, which was the coils actually, and then we looked at a ZVS buck, and then we looked at an inverter, a resonating inverter, something like this, series resonant inverter. The reason it's called series is these elements turn out to be in series with each other. The resonating L and the resonating cap and the load are all in series with each other. So we looked at this one as well. If you actually, the performance of most of these converters depend on the quality factor you choose, and also the relationship between the switching frequency and the resonance frequency. So as you can see, for instance, here, if the switching frequency and the resonance frequency are exactly the same, you get the highest, for instance, gain. But if you deviate from that, it's going to get a little bit different. And obviously the quality factor. Then we analyzed this one, which is called the series resonance DC to DC converter. If you can see on the left side, we have like a H bridge or a half bridge on the left side, giving us a square shape. On the right hand side, we have a diode rectifier, but you can easily make this converter a bidirectional converter and have actually another H bridge over there. Topologies like this are called DABs, dual active bridge converters. So you have basically two bridges on each side. And then in between, we have this resonating inductor and a resonating cap placed in series. Therefore, the name comes from series resonance. And we are going to take a look at some of the waveforms, not now, but after I'm done with this review. As it turns out, you can argue that the current that is passing through this inductor is almost sinusoidal if the switching frequency and the resonance frequency are very close. And then if you, for instance, only look at the fundamental harmonic of the square shape signal that is being generated from this point to this point, and also the square shape voltage that is being generated from this point to this point, and look at only the harmonic components, the fundamental harmonic component of them, you can actually find a kind of a voltage transfer ratio, something like this. And if you plot it, it is going to look like this. Again, typical graphs. If the switching frequency and the resonance frequency are close to each other, you have a high gain. And also, if you deviate from each direction, your gain is going to go down a little bit. And also, it depends on your quality factor. If the quality factor gets better and better or increases, you are going to actually have a more sensitivity to the difference between the resonance frequency and the switching frequency. The quality factor is dependent on the value of your load, but sometimes it also depends on the examples that I had last time in terms of wireless charging. It depends on the mismatch that you have. For instance, the example that I had for a vehicle being parked to get charged wirelessly, depending on the position of the vehicle and the position of the base and how much they are misaligned with each other, that actually impacts the value of Q. Then the book continues and looks at these topologies, looking at the fact that, for instance, where your switching frequency is with respect to your resonance frequency. If it is half of less than that, if it is way far from it in terms of being a small, which we didn't really analyze in here. This is another example of the same topology. The only difference is instead of using 4 diodes to rectify the output signal, it is using a center tapped actually rectification scheme. Then another topology that we are not going to really get into details is this one. It's pretty much similar to the previous one. The only difference is you are using a relatively large inductor over here, which is like a current source. Then your resonating components are this inductor over here and this capacitor over here. Other than that, it's pretty much is the same. On the left-hand side, you have a half bridge to create a square-shaped voltage signal from here to here. And over here, because we have a current source, you can argue that the current that is going out is now kind of a square shape. It's like having a rectifier, but the output of this rectifier is a DC current. So on the input of the rectifier, you have a square-shaped current like this. And you can argue that the voltage across this resonating cap is almost an AC voltage. So that's actually how it's being rectified. And because this is an AC voltage, you can also argue that this would be a good place to place a transformer here as well in case you're looking for an isolated approach. You know, the input and output sides are isolated or detached from each other. So the same trend continues. You, for instance, you have a square shape voltage over here. You can only focus on the fundamental harmonic of this square shape. And also you have a square shape current over here that you can focus on the fundamental harmonic of this current and then write a bunch of equations and in the end find a voltage transfer ratio like this or like this. I mean, this is just this same math basically. And if you plot it, again, you can see if your switching frequency and resonance frequency are close to each other, you have a relatively high gain, and also gain is dependent on the value of your quality factor. So as the quality factor increases, your gain is going to increase and increase. And so is the sensitivity to the mismatch between the resonance frequency and the switching frequency. The third one, again, we are not going to get into the details of this, is almost the same thing. But this one is called a series parallel DC-DC converter. By the way, the reason that this was called a parallel converter is you can argue that from this point to the right, you almost have a resistor equivalent kind of a thing. And this resonating cap is placed in parallel with that. So that's why the term parallel resonance comes in. And this one is a series parallel, which is kind of a combination of the two. So the resonating components are this cap over here, this inductor over here, and this cap over here. Again, on the output side, we have a relatively large inductor, which can be modeled with a constant current of I out. And then similar things from here to here. By the switching pattern that you choose, you are generating a square-shaped voltage. And on the output side, IB or I out or whatever you name it is a square-shaped current. And then you can actually analyze the system and find another voltage transfer ratio which looks like this. And if you plot it, it looks like this. It's a little bit scarier than the ones before, but again you can see that the point that the resonance frequency and the switching frequency are matching with each other. All of these curves cross each other, but at the same time, if your quality factor is 1, for instance, you can achieve a relatively large voltage gain. All right, then the chapter moves on towards the third category of resonance converters. So far we have looked at switch resonance like ZVS buck and ZCS buck, the load resonance converters, the parallel and the series parallel that I just talked about, and the final one is the resonance DC link converters. Historically, a lot of times you have a relatively large cap over here to maintain a DC voltage and kind of buffer between the upstream converter and the downstream converter. Now, this category of converters, instead of having a capacitor that is holding a DC voltage, they are actually manipulating things in a way that it actually holds an AC voltage. The advantage is if you have a DC voltage, then your cap should be an electrolytic cap. It might be bulky, it might be expensive, and it may not be very reliable in terms of its lifetime. But if you manipulate it so that the voltage of this linking capacitor is an AC kind of a voltage, then you can argue, for instance, you can reduce the size of the cap, or in terms of lifetime, you may actually find a better option. So technically, this could be the upstream converter, this could be the downstream converter. The downstream converter or the circuitry is modeled with just a current source, and the upstream converter is modeled with a kind of a DC source, and then in between we have these resonating elements. So technically, in a practical case, if you don't have this, you just have this cap in between the converters. But now we have this resonating inductor added, and this cap is behaving like a resonating cap, and the size of this cap is much smaller than this cap over here that is withholding a DC voltage. So we are not going to again go through the details of that. I'm just mentioning this so that you would be at least familiar with the terminology, resonant DC link approaches. So technically what happens is when this switch is closed, you are basically energizing this inductor. So the current of this resonance, the resonating inductor rises almost linearly like here. And then when you open up the switch, so now when you open up the switch, what happens is now we have a resonance between LR and CR, and the result of that resonance is a waveform like this, or a waveform like this. Okay, and in terms of the current of the inductor, it looks like this. So you can argue that we have the switch over here. If I focus on the voltage across the switch, which turns out to be the voltage of the cap as well, you have ZVS here at turn off of the switch, and also ZVS over here at turn on of the switch. So things are happening in terms of soft switching at a ZVS manner. In terms of your input current is still almost a DC current. So this is your input current. Over here it is almost a DC current, which is fine. Ideally, you would like to draw a DC current from a DC source, and this is almost happening here. And that's it. So then you can. This was just a very simple kind of a concept circuit. Then you can apply it to different topologies. For instance, you can apply it to a three-phase inverter that you have seen before. If I just take this thing out and take this thing out, this is the familiar three-phase inverter that you have seen before. But by adding these two, basically what happens is we can manage to have. So by adding this resonating cap, this is going to be looking like this. Just a bunch of resonance sequential resonances. And for instance, if I measure my VAB voltage, my line-to-line voltage, before it was like a PWM square shape kind of a thing, now it could be like this. All right. And then you can argue that, oh, I'm focusing on the fundamental harmonic of this guy, which is a sinusoidal current. So this may improve some of the noise issues or some of the commutation issues that you have between the switches, because now the commutation is happening at 0 voltage. So it actually gives you an opportunity to turn the switches on and off when there is not a lot of voltage stress around it. And this is it. This is the end of the chapter. So we didn't really cover everything in this chapter. We only covered ZVS buck, ZCS buck, and the inverter, and also the series resonant converter. Now going back to that series resonant DC to DC converter, let's look at some of the waveforms that should be corrected. So what I'm doing is I'm focusing on the voltage from point A to point B. According to my switching pattern, it's either Vin over 2 or negative Vin over 2. That's the voltage of either this cap, which is Vin over 2, or the voltage of this cap in a reverse manner, which is negative Vin over 2. And on the output side, if I actually assume that this current of this inductor is almost sinusoidal, then I have a kind of a square-shaped voltage over here, depending on if DR1 and DR2 are the ones that are conducting. Therefore, VCD is V out. Otherwise, DR3 and DR4 are the diodes that are conducting, and therefore VCD will be negative V out. So technically, I have a square-shaped voltage on the input side and output side. All right. Okay, let me just B, is it okay, A and B. So this is VAB for 2 periods. Here the level is Vin over 2. And here the level is negative Vin over 2. All right, so this is VAB. VCD is almost the same thing with a little bit of a phase shift. And there is a reason that we have a phase shift, because if you analyze an RC circuit over here or LRC circuit, the current of the inductor is shifted from the voltage of the input. It actually lags a little bit. All right. So now this phase shift is this much. All right. So technically, I'm assuming that this is my ILR, the current of the resonating inductor. It is almost sinusoidal. All right, something like this. And because of this, when this current is positive, it pushes DR1 and DR2 to conduct. And when this current is negative, it pushes DR3 and DR4 to conduct. So if I look at voltage from C to D, when the current is positive, VCD is V out. When the current is negative, VCD is negative V out. So when it is positive, it's V out. And when it is negative, it is negative V out. All right, so this level is V out, and this level is negative V out. So technically, we are generating 2 square-shaped waveforms with a little of a phase difference between them. All right, now, for instance, we were looking at the current of a particular switch. So I'm focusing on switch number 1. And by the way, I'm not including the diode in my switch. So when I'm looking at the current of this switch, I'm looking at this current over here, IS1. So if I'm interested in plotting that, okay, this switch, basically this switch and the diode only conduct when the current is positive. So from here to here is my action area, as well as from here to here. Otherwise, this whole thing is not even in the picture. And this switch is only supporting the conduction of the current when a VAB is positive. So from here to here, I actually have a command for the switch to turn on, or maybe the diode is on. So the bottom line is this is going to be your current waveform. All right. Before that, you still have some current going on, basically, this portion of the current. But this portion of the current, because it is negative, is actually flowing through the diode. So if I plot the current of the diode as well, let me just plot the diode current as well. Let me call it ID1, and this would be IS1. Okay. So this would be the current of the diode. This whole leg is shorted, but you have to focus which one of them is conducting. When the current is negative, obviously the switch is not supporting, assuming that this is, for instance, an IGBT, and the diode is the one that is conducting, and then there is a commutation happening between the diode and the switch, so you have to be careful when to turn your switch on, and this goes on over here. And then not much is going on until this other so this would be the current of your diode, of your switch. And as long as the diode is concerned, I'm plotting this portion over here. Oops, actually I made a mistake. This is not the current of the diode, this is the opposite of the current of the diode, because the current of the diode should always be positive. All right, so this is the opposite of the current of the diode. All right, so the current of the diode minus the current of the switch, or the current of the switch minus the current of the diode, should support this portion of my conduction, as well as this portion. And it is actually doing that. Then you can focus on ZVS and ZCS and things like that that we discussed last time. All right, so this was a correction of the waveform that I drew last time because there was a mistake in there. All right, any questions so far? Okay, so what we are going to do now is we are going to go to the new chapter, chapter 10. This chapter is basically covering a little bit of a practical stuff, as long as when you want to go to the lab and actually build a converter. There is way more to building a converter than is covered in this chapter, but just the very basics of how a converter is built. Okay. One of the topics is, okay, you have a switch. So in this class, we often say we turn the switch on, we turn the switch off. So the question is, how exactly do we turn the switch on or off? So let me go back to OneNote, actually. Just write it over here. Chapter 10. All right, so the switch that we are talking about is either a MOSFET, like this one is an N-channel MOSFET, or an IGBT, like this one is an NPN IGBT. Okay, so technically when we say turn the switch on or off, we mean that from gate to source of both of these devices, you can argue that there is a cap. It's like an internal kind of a cap. If you charge this cap beyond the threshold voltage, and the threshold voltage is, for instance, 5 volts. If you charge this cap to beyond that voltage, your switch is going to turn on. And if you discharge it to 0, or sometimes to a little bit of a negative value, like negative 5 volts or so, your switch is going to be turned off. So it's all about charging and discharging the cap. Now, because you want for your switching to happen very quickly, you have to charge and discharge this capacitor very quickly. Okay, and by the way, the name of this cap is CGS, capacitor from gate to source. All right. In terms of values, it's like several picofarad, or maybe, I don't know. I have to look at the data sheet, but it's like either pico or nano. It's not like a microfarad. It's a relatively small cap, but then you have to charge it and discharge it as quickly as possible so that you can actually turn your switch on and off as quickly as you can. So that's why you have a gate drive circuit, basically. So technically, if you have a control circuit, okay. So the job of this controller is to create, for instance, your PWM signal and provide regulation, for instance, by comparing your output voltage with the reference and creating some error signal. And we have already talked about it, like an error amplifier and stuff like that. In the end, this controller gives you a PWM signal which is determining the switching pattern. If this switch is at the high level, that means the switch should be on. If it is at the low level, the switch should be off. So one thing that you can do is you can directly, and first of all, remember, this is grounded most of the times. And remember, your controller needs its own power supply. So this would be voltage source for the controller. All right. One solution would be directly connecting this to your switch, assuming that you have a switch that has a source grounded kind of a topology, like a boost topology. All right, remember, in the boost topology, the source is grounded, so no problem. Our controller is generating a signal with respect to the ground, and our switch also has its source grounded, so we can just directly connect them to each other. Now what happens here is, it may work, it may not work, depending on the controller and how much current this controller can sink or source. Remember, we want to charge this cap very, very, very quickly. But sometimes the output stage of your controller cannot sink or source a lot of current. We're talking about a very small cap, but sinking it with, for instance, 2 amperes of current, or sourcing or draining out 2 amperes of current out. And sometimes this controller is not really designed to do that job for you. So you can see that your switch is going to turn on and off, but there is going to be a little bit of a time delay and a kind of a slow transient. And actually in this chapter, there is a figure showing that. When you directly connect your controller to your switch, you can see for instance here, your switch is supposed to turn off, but you can see it takes forever for the switch to turn off. Versus, if you do a good job, it should be very, very instant. A very sharp rise. So this is because you're not charging your cap, your gate to source cap, as quickly as it should be charged. You can see over here, a good job is being done. You discharge it very quickly, therefore the switch turns off very quickly. And then you charge it very quickly, therefore the switch turns on very quickly. Versus over here, it takes forever to get discharged, and to get charged, and also to get discharged. So for this reason, there are some controllers that already have a good output, basically a stage that can actually sink or source a lot of current, up to several amperes of current for a very short period of time, and some of them don't. So if you are working with a controller that doesn't have that stage, what you got to do is you got to add an extra basically layer in between these two guys, which is called the gate driver. So the job of this gate driver is look at the commands of the controller and then provide a very high impulse of current to charge this cap, or very draining kind of an impulse of current to discharge the cap. So then you have basically a gate driver. So let me redraw this now. So gate driver doesn't really change anything in terms of, as long as the control is concerned, it just repeats the same thing. It looks at the commands that the controller is sending out, low or high, and then kind of amplifies that in terms of power or current capability, and then sends it to the switch. And again, the gate driver needs its own power supply. And probably, it doesn't necessarily need a ground, but assuming that you already have a ground here, this should be ground as well. All right, so this is a chip that you can actually purchase for, I don't know, less than $1, and there are many of them available in the market, and here are a few examples for them. Let's go back here. So, for instance, one way of doing that is using this, push-pull kind of a structure over here. So the job of this push-pull is, it looks at its input, this is the command that is coming from your controller, and then depending on the level of the command, either Q1 is on or Q2 is on, and these transistors are high current, basically transistors. So what happens is, for instance, when this Q1 is on, you have a very good basically current path over here to charge this gate to source kind of a cap as quickly as possible. So you have a very sharp impulse of current over here, and then when you want to turn the switch off, Q2 turns on. So technically what happens is you have a very sharp impulse of current in this direction now. So very quickly you can charge the cap, or very quickly you can discharge the cap, and the controller has nothing to do with that. The controller is not really seeing this current. It's just this basically a totem pole or push-pull circuit that is seeing that. What we have to be careful about is, by doing so, sometimes we are also inverting our signal. So remember, some of the gate drivers that you may purchase, they are actually acting as an inverter as well. So some of them are like just a buffer. There's no inversion of signal involved, but some of them are actually inverting the signal as well. So you have to be careful about that. And remember that the controller needs its own power supply. Now this power supply should be able to handle a high impulse of current. So for that reason, if this is a chip over here, you usually add an extra cap over here as well, and this cap is actually providing that extra amount of current. It is a combination of an electrolytic cap and a high, low internal resistance ceramic or a filmed kind of a cap. So the reason that you're doing that is your main source, which could be further down, may not be able to handle high impulses of current. So locally you add a cap over there to do that. So even though this current is a pulsating current, over here you can see it's much smoother. And that means if there is other stuff connected to this source, they are not going to see as much noise. So this was all about it, but remember, in all of these examples, you're assuming that your transistor has a source pin that is connected to the ground. All right, and what if that doesn't happen? For instance, okay, here is more examples. Instead of a push-pull with an NPN and a PNP transistor, you can use two NPN transistors like over here, or these transistors do not necessarily have to be BJTs. They could be actually FETs as well, like the examples that we have here and here, and also here, but it's almost basically the same thing. All right. Now, sometimes it happens that your switch is kind of a floated switch, like the buck topology. Let's go back here and take a look at that. Oops, here. All right. So this would work very well if you are trying to build a boost converter. Okay. Now, if you're trying to build a buck converter, things are different. As you can see, the source pin of the switch is not grounded anymore, okay? Because most of the times, this is your ground. And your controller is also using the same ground. So this is the ground that the power stage and the control circuitry, they are both sharing together. And unfortunately, this source has nothing to do with the ground. It's not really grounded. So if you just use a gate driver to directly connect that to the gate, it's never going to work. You cannot really turn the switch on and off. So technically what happens is, remember, this cap that you have to charge and discharge exists between the gate and the source of your transistor. So your gate driver should also be connected to those two pins. So if I have this gate driver over here, okay, so one pin goes here, the other pin goes here, and the gate driver has its own VG, or its own power supply, with respect to another pin. So technically you can imagine that there is a kind of a battery existing over here, and this battery is kind of a floated battery. It has nothing to do with the ground of your system. And then this gate driver gets the commands from your controller. And the controller is connected to the same ground and has its own power supply. Okay, so all of a sudden you see, in the worst case scenario, you may need 3 power supplies. One power supply is your main source of power that is delivering the power to your load. One power supply, like this, is a floated power supply that is floated. It is not grounded. And then there's a third power supply for your control circuitry. Sometimes these two could be the same, depending on the level of your main power supply. If your main power is like 20 volts, you can find a controller that operates at 20 volts, so you can actually use the same source for 2 purposes. But if this DC source is a 400 volt DC, then you cannot find a controller that operates at 400 volts, so you need to have another power supply which gives you, for instance, 15 volts for your VC over here. This guy over here, there are ways of implementing this. One way is having a dedicated DC to DC converter to get the power from here, or maybe here, and push it over here to a cap. For instance, you can use a flyback converter to do this for you. Okay, flyback provides isolation, so you can actually use, on the primary side, you're connecting things to your main power supply or to your controller power supply. On the output side, you just have a cap which is providing power to your gate driver. So this could be a flyback converter right here. So the flyback converter has nothing to do with the process of the main power. What it is being used for is to provide power for your gate circuitry. Or you can just use a battery, like a floated battery, assuming that you're just experimenting in the lab. You're not really putting a product out there because the battery is going to run out and you have to replace it. So what most of the students do in the lab is just they use a 9-volt battery and then charge it at night and then put it there. And the good thing is that it doesn't have a lot of noise in it. Or there are approaches that you don't have to use the battery, or you don't have to use an kind of build your own flyback converter. And so these approaches are called high side drivers. Okay, so as you can see, they are connected to the ground. You can see the switch is not grounded here anymore. But still they can do the job for you with respect to a controller that is also grounded. All right, how does this one work is, when this signal is active, basically, what happens is you are charging the cap over here. All right, when this S1 and S2 are both on, basically, or when your controller is sending you a high command signal. like figure B over here. So you can see the cap gets charged. And basically the other thing that is happening is you can see from here I'm connecting to the ground, and from here I'm connected to the ground. That means from gate to source I'm not applying any signal. So my switch is off. My main switch is off over here. Then when the low signal arrives, both of S1 and S2, these two transistors, turn off, like here, they're off. And what happens is now we are applying this cap voltage across the gate to source. So now this cap is actually your power supply to power up the gate and turn the gate on. So this is called a bootstrap circuit. There are chips out there that actually are doing this. They're called high side drivers. And unfortunately, I personally have never had luck with these. You buy them and they never work well, as good as you expect them to, unless you really have to be careful about reading the data sheet very, very good. The other trick that is here is that you have to pay attention to is when your switch is off, the assumption is that the source of your transistor is grounded. So if you're using a topology that the source of your, like in a buck converter, that's fine, because when the switch is off, the diode is on and the source is grounded. But if you are in a topology that does not happen, you have to be very careful about using these bootstrap high side drivers. They are called high side driver because the output side is like a high side kind of a voltage. So this way you're avoiding using a flyback or an independent floated battery. And you can buy chips. For instance, this is a product out by International Rectifier, which is actually doing the job for you. And sometimes you have two kind of transistors kind of complementing each other. And then there are chips out here, which is IR2110, this one, which has one high side and one low side driver in itself. So technically what it does is you can see this transistor, no problem. It's a low side switch because the source is grounded. This one, the source is not grounded. Imagine you want to try to build like a half bridge kind of a circuit. You have two transistors. One of them is grounded, no problem. A low side gate drive would do it. The other one is not grounded, so you need to have a high side driver. So there are solutions out there you can just purchase, and it's very, very important to have these caps over here. Do not just neglect them because they are very, very fundamental in the operation of the converter, of the gate driver. All right, so this is all about a little bit about gate drivers. Another way of providing this isolation, sometimes by isolation I mean your controller over here is isolated. For instance, you have an isolated converter, so your feedback loop also has to be isolated as well. And one way of providing isolation is using a transformer for your gate driver. So technically your controller is generating a square shape or whatever kind of waveform, but the ground here is not the same as the ground here. So they have different grounds. So your controller is kind of isolated from your power stage. The problem with these guys is transformers do not transfer DC signals. So on the output, if you look at this voltage over here, it is not really DC. It doesn't have any DC component in it, and it has an AC. And depending on the value of your duty cycle, the level of the signal goes up and down, and sometimes the level goes so down that it's not high enough to overpass the threshold of the gate capacitor voltage to turn the transistor on. And sometimes they are slow, so there are challenges here as well. Or sometimes what you can do is you can use an optocoupler, okay, which provides isolation. There is optics in between, so electrically this side of the system has nothing to do with this side of the system. So you can see your gate driver is here. Your gate driver is providing that push-pull kind of a mechanism to charge or discharge this capacitor very, very quickly. You have your own power supply over here, which is connecting here to here. But the whole thing is isolated from your controller through an optic couplers. Okay, so you can see optic couplers are also available on the market, and sometimes this whole thing is integrated together, so you don't have to buy two separate chips. One of them is the optic coupler, the other one is the gate driver. They are combined together, and you can just use them. All right. The other thing, the other things that you may see in a gate drive circuit is sometimes you see. Let me go back. You see a bunch of resistors. So for instance, this is your gate driver. And sometimes when you look at the circuit, you see that there is a resistor added here. So the purpose of this resistor is, if you turn the system off, not necessarily the gate driver knows that you're turning everything off. So basically you're disconnecting the power from your gate driver. At the time that you were doing that, if this capacitor was charged, the gate driver just turned off. It doesn't have the opportunity to discharge the cap. So you have turned the system off, but your switch is still on, and that may not be a good thing. So what this resistor does is, it doesn't interfere with the regular operation of the system, but if you turn the system off and keep the transistor on, gradually discharges this gap, and gradually after, I don't know, 10 milliseconds or so, for instance, this turns off, for instance. So this is just for protecting the system, that you have turned the switch off, you have turned the power off, assuming that everything is off in the system, but some of the transistors in the system may still be on. And in order for this cap not to interfere with the normal operation, it's usually in the order of like kiloohms, like let's say 10 kilo ohm resistance is a good one over here. And sometimes you see even a resistor over here as well, like a 1 ohm, a 2 ohm, a 3 ohm, a 5 ohm, sometimes a 10 ohm resistance over here. This is just to limit the current. Okay, you're just putting the current, the resistor in series with your cap, so that you're limiting the current, because ultimately the current that appears over here is the current that you're drawing from your source. And if your source is not capable of handling, impulses of current, then it may create some noise somewhere else that is going to bother the system. So you add a little bit of resistance over here to cut out the peak value of this current. Other than that, it doesn't have any functionality. All right. So this was all about gate drivers. So you can see that just the simple phrase that I said, oh, we turn the switch on or off, in practice, it takes a little bit of experience and some engineering aspects. If you're interested, you can take the power electronics lab next semester, and you will see more of these things over there. The other thing that I wanted to talk about is snubbers. Okay. Again, you may look at the design of someone else and see that they are, for instance, building a flyback converter. Remember, it was something like this. For instance, they are using an IGBT over here. Arc. So this is the flyback converter that you have seen before. But then you see there are a bunch of extra elements in the system. For instance, there might be a diode here, a resistor here, and a cap here. And then you wonder, oh boy, what is this one? I mean, why are we adding these extra components in the system? Or many other topology that you see across the switches, there is a bunch of extra components. What these guys do, in general, they are called snubbers. And what they do is they protect the switch from, sometimes depending on what the purpose is, over voltage or over current stress on the switch. Now, flyback is the most notorious one, because if you don't really do it, you can easily harm your converter, your switch. Now, why is that? The reason is this transformer that we have built over here, what we want this transformer to have is behave like an ideal transformer and a magnetizing inductance that we are going to use as the main inductor in the system. However, as you're building this, you're also, whether you like it or not, this transformer is going to have some leakage inductance. All right, something like this. Now, why is this leakage inductance? Why does it exist? The reason that it exists is going back to 205 is so let's say this is your primary side and secondary side, and you have a magnetic core, and you're applying a bunch of current, and this current creates some flux that links to the secondary side. So that's actually the transformer works. However, there might be some flux generated because of the current on the primary side that is not really linked to the secondary side. It's just of its own. It's circulating around just the primary side. It is not linked to the secondary side. And that is called the leakage inductance. And it's always there no matter how well you design your system. And it may actually do some harm to you guys because it's like an undesired component in the system. Unfortunately, in terms of values, you can actually design the system that, for instance, if you need a 100 microhenry inductor as your main magnetizing inductance, this leakage is around usually between 1 to 5%. So let me call it 2 microhenry. So it's a relatively small inductance, but it exists. Now the fact that it exists is ideally, okay, let's say this doesn't exist. Okay. Ideally, when you focus on this voltage from drain to source of the switch that you are using, whether it's an IGBT or it's a MOSFET, it doesn't matter. Ideally, it is supposed to look like this. In the first mode, the switch is on, so it's almost zero. In the second mode, it looks like this. And this level, if you remember, it was Vn plus, I think, N1 over N2 V out. Okay, something like this. Okay. Now, if you consider this leakage inductance existing, what happens is when you open up the switch, okay, when you open up the switch, we have current right before that. You have current here and here. For this current, no problem. It circulates around here. And that's actually how we analyze the system. So no problem for the current of the magnetizing inductance. But for this current, it has nowhere to go. And what it does is, well, you definitely have some parasitic capacitance around your switch. Now, because the switch is off, it chooses this parasitic capacitance to flow through. So technically, as soon as you turn your switch off, this magnetizing inductance pushes like this. So it starts kind of resonating with this parasitic capacitance that, again, whether you like it or not, it is always there, that is from your drain to source. Now, this cap is also a small cap. It could be, for instance, 0.5 nanofarad. And you can look at the data sheet of the particular switch that you're using, and you can see how much it is. So ideally, you would expect something like this for your switch. In reality, what happens is you see a huge spike and a bunch of resonance going on, something like this. And the spike is basically the energy stored in that leakage inductance is being released into this cap. Therefore, the voltage of the cap rises, and then some oscillation is going on, and you see a system like that. So before, you were designing the system and say, oh, for instance, this is only, I don't know, 100 volts. So if I buy a 200 volt switch, I'm going to be fine. But then you realize that the first time that you build a system, your switch is dead because your switch was only capable of handling 200 volts, but then this was like 1,000 volts. It is a very short period of time, but just a little bit of an extra voltage may actually harm your switch. So you can see that your switches keep getting killed, basically, and that's actually the reason. To protect the switch from this extra voltage, you add the snubber to the system. Okay, so the reason that you're adding the snubber is not to improve the efficiency or provide ZVS or Z. Sometimes they do, but most basic reason is you're trying to protect your switch from over voltage. All right, so how does that one work? All right, let me redraw this. This is getting really busy. So we have this leakage inductance, and this is your magnetizing inductance, and this is the primary side of your transformer. And remember, you don't really have access to any of these terminals. The only terminal that you have access to is here and here. Okay, so remember, these are all modeling your transformer. They are not really discrete components. Okay. So this is the primary side, okay? All right. So what you do is you add a cap to the system so that instead of the parasitic cap of the transistor getting charged from this leakage energy, that extra cap is going to be charged. So you add this cap over here, and then I'm going to explain why. You add a diode over here and a resistor. All right. So now what happens is when you open up the switch, this energy that we have over here is going to get released. It's going to push this diode to turn on, and it's going to get this cap charged. And now, because you're using a larger cap, remember the parasitic cap is a very small cap. And that's why the voltage rises so much, because there's only a little bit of energy is needed to rise the voltage of this cap to beyond the tolerance of the switch. But then you can use externally, you can use a larger cap over here. For instance, you can say, let me see what I use. I have simulations for this as well. I just want to see how much I use over here in my simulation. It's like 10 nano, 10 pico. Yeah, 10 nano. So now you're using a larger cap over here. That means with a certain same amount of energy, the voltage of this new cap, because it's larger, is not going to rise to like 1,000 volts. It's just going to be further limited. So when you open up the switch, this is the path. Switch open. All right. Now when you close the switch, what happens is, now your switch is like a short circuit, and remember, we just charged the cap. There should be an opportunity for this cap to get discharged as well. It is going to go this way. So this would be the path for switch closed. All right. Okay, something like this. So when you open up the switch, in order to hold the voltage to a certain tolerable value, you add this external cap, and this energy is stored over here is going to charge up the cap. And then when you close the switch, this energy should be released somewhere, and basically it is going to get released. Part of it will be released in this resistor, and part of it will be released in the internal resistance of your switch. So you can see you're actually adding a little losses to the system, and for what cause? To actually protect your switch. This resistor over here, so technically you can see on the switch enclosed kind of a thing, you have an RC system, right? So the time constant of this should be much smaller than the period. So for instance, the value that I have chosen over here is 5 ohms. Oops, what happened? Okay, Technically, you don't really need this resistor over here. You can argue that I just put another diode over here. You can say I can do something like this. When the energy comes, I'm going to charge the cap. And when it comes to discharging the cap, I just use another diode. And then it gets discharged when you close the switch. But the problem with this approach is the energy that is stored in the cap is going to get released in the internal resistance of your switch, so your switch is going to get warm. Versus here, the energy released, at least most of the energy stored in this cap, is going to get released in this resistor. So it's externally dissipated. It is not internal to the switch. So the whole thing is you have losses in the system. The question is where you want this loss to be dissipated. Do you want it to be dissipated in your switch? Therefore, you have to get a larger heatsink for the switch, or it is going to get dissipated in this resistor. Okay, something like that. So this system over here is like called a snubber, basically. This is it. This is called a snubber. I don't know if I have a good color over here. All right, so this is kind of voltage snubber because it's protecting the voltage of the system. So, you know, instead of having an ugly waveform like this, the black one over here, your waveform is still ugly, but it's not as ugly as you was before. So now you have a system like this. Ideally, you would like to see something like this, but practically you see, with adding the snubber, you see something like this. Something like that. And you can see now your voltage is limited to this much. Okay. The larger cap you use, the snubber cap over here, the larger this cap is, the smaller this peak value is going to be, which is good. But at the same time, the longest it takes to rise. So if you use a very large cap, this is what's going to look like. If, for instance, in this example that I have, this cap is 10 nanofarads. Let's say if you use 100 nanofarads, what's going to happen is it's going to take a longer time for this cap to get, you know, charged. And sometimes it's not a good thing because it interferes with the rest of the signal. Ideally, you would like to see a square shape kind of a signal over there. You don't want it to deviate a lot. So this would be larger C, smaller C. But if you keep getting your cap smaller and smaller, it's as if you don't even have a cap. You're going back to the original case that the parasitic cap of the switch is actually the only thing that is holding things together. All right, any questions? So this was all about the snubber. Sometimes you add the snubbers to protect the system from over voltage. Sometimes you know, you do it to protect the system from over current, especially in older power electronics of the 70s. Basically, they used SCRs, and SCRs are very sensitive to high DIs over DTs or DV over DTs. So that's why back then, if you talk to an engineer who has been in this industry for 20, 30 years, they know a lot about snubbers and over current protection and over, you know, voltage protection, because the switches that they used to work with are very sensitive to those problems. Nowadays, things are better. Sometimes you see things like that for a particular topology, especially flyback is the most notorious one, because you are using an inductor, a transformer, and the leakage inductance is going to actually cause some problems. I have some simulations here as well. Let's actually take a look. I don't know why it's black. I have to log in again. Okay. So what I have here is, I'm going to post this on Blackboard. I have just a classic case of a converter. Everything is ideal, and things are going to look nice, but this is not really what you're going to see in the lab. Then I add this leakage inductance over here. If you add this, the software is going to give you an error, because practically what you're doing is you're violating the conservation of energy. You're energizing this leakage, then you open up the switch, and this energy has nowhere to go. Therefore, you're going to get an error in your software. Let me see if I can do it actually. Delete. Okay, so this is just a bare bone flyback converter that we have analyzed in the class, and the waveforms that you are going to see are very similar. Here the input voltage is 50 volts, the turns ratio of the transformer is 2:1, and the duty cycle is 50%. So technically you can do the math and see your output is going to be around 25 volts, which it is. So you're getting half of your input voltage. And this is the voltage from drain to source of your transistor, and it looks very, very nice. It's either 0 or 100 volts, which is Vn plus and 1 over N2 times Vout. And 1 over N2 is 2, Vout is 25, so it's 50 plus 50, 100 volts. So things look very, very nice. But when you go to the lab and all right, build this. Let me close it and open it again, or maybe I can just do and build this. Things are not going to be as good, so I'm going to actually go one stage further and add this leakage inductance that in reality is always there. Okay, now if you try to run this, you're definitely getting an error. Are going to get an error because there is energy over here, and then you open up your switch and that energy cannot really get released to anywhere. So you get an error like that, and in order to make it more realistic, what you can do is you can say, oh, I forgot that my switch basically has some parasitic capacitance, and this parasitic capacitance is very, very small. For instance, here it is only half a nanofarad. So now let's see what happens. Okay. Now, unfortunately, the system is going to get really slow because all of a sudden you're adding a very small cap to the system, and in order for MATLAB to calculate that, it has to use very small time intervals, and your simulation is going to get really... So first of all, you don't get an error, which is good. So technically what's happening is this leakage inductance is not releasing its energy in this parasitic cap. And I have also added a resistance over here because whether you like it or not, the primary side of your winding has some internal resistance as well. Like here, I have put 0.2 ohms of resistance. Now, first of all, you can see the simulation is very small. It is supposed to go ultimately to 25 volts. It's only at 1 volt. But you can actually observe that we are in trouble, and you can see this is the voltage on your switch. It goes to a very high spike. In this particular case, it's 2800 volts. Once it settles down, things are going to get better. And the resonance is so bad, it actually comes back to 0. So technically, you were expecting to see a square shape over here, but you see something like this. And you can actually see in the lab, you can actually see something similar to this in the lab. Now, what you do is you add your snubber. Let me delete this. So let me delete that one as well. Okay, now I've added my snubber, my diode, my resistor, which is 5 ohms, and my cap, external cap, which is 10 nano. Now, if you run it, it is still, okay, it's faster. You can see it's getting down. Because I eliminated that parasitic cap, I'm assuming that the parasitic cap does not exist. Otherwise, it's going to be slow. My output voltage is still going to 25 ohms, so the addition of this snubber hasn't really messed up with my steady state analysis. And if you look at the voltage drop across your switch, it is something like this. So it still goes to 150 volts, but it is much better than going to 600 volts. So you can argue that here I can purchase a switch, which is a 200 volt switch, and it is going to do the job for you guys. So I'm going to post this on Blackboard as well. If you want to mess around, you can do it. All right, so we are done, I guess. How many of you guys are graduating? Okay, well, congratulations, and we are going to miss you guys. The rest of you guys, I'll see you back in January. I have the quiz graded over here, as I said at the beginning of the class. This evening or tomorrow morning, if you look at that Blackboard file, you will see your final grade incorporating your class attendance as well. So you can see I'm looking at waiting for the last sheet to be completed. And I'm assuming that you are not going to take the final exam. So if you see final grade, your final exam grade is 0, because that's my assumption. Then you can plug in your own number that you expect to get and see how you can improve your grade. Please remember, the final exam, it has 30 points. The sign-up sheet is over here. Don't forget to sign your name.